So we were working on obtaining properties for normal shockwave relations for a one-dimensional flow, basically straight streamlines, that is, and adiabatic flow, so there's no external heat transfer and it's steady state and inviscid flow. And we actually did obtain relations for Mach 2 after the shock wave, and P2 and temperature and density after the shock wave, and also this one gives us enthalpy change. We do know one fact, we have been discussing it for some time now. The stagnation temperature does not change because it's an adiabatic process. It is an irreversible process though. So it's an adiabatic irreversible process, as we discussed also yesterday. So it is not an isentropic process, adiabatic and irreversible. So it's not isentropic, meaning that entropy also will be different. S2 will be different than S1. We don't know how to calculate it yet. We will see that today. And what else? Stagnation temperature is constant, so therefore stagnation enthalpies are constant for a calorically perfect gas. This is just H01. I'm sorry, H01 is Cp times T01. Similarly for H02. So basically we have two more properties left that we need to understand. The first one is the entropy equation. We need an equation for entropy. And the second one is what will happen to stagnation pressure, because stagnation pressure at 2 will not be equal to stagnation pressure at 1 because of this case, because of irreversibility, meaning and the irreversibility is due to the strong viscous effects happening within the shock wave, inside the shock wave. So that creates basically it's so friction related, it creates basically irreversibility. So that changes stagnation pressure. But what is the equation for that? We need to calculate. So basically, today we're going to discuss these two, S2 and P02. So if we can remember, we already actually have an equation for entropy change between two states. If it's a non-isentropic process, for delta S entropy change. So if it's a non-isentropic process, this means that S2 minus S1 must be positive. So there must be an entropy increase actually. So it is actually a function of temperature and pressure at 2 and 1. Let me remind you the equation again. So this is Cp ln T2 minus 1 and T2 over T1 minus R ln P2 over P1. We obtained this previously. Now, since this is a function of the temperature ratios and the pressure ratios, and we do have their changes with respect to as a function of Mach number, basically inlet Mach number, and this one also as a function of inlet Mach number. We obtained those yesterday. If we plug in those functions, now we directly obtain a relation for the entropy change across a shock wave, a normal shock wave. So let me write the equation. If you plug in the Mach number functions for the temperature and pressure ratios, the equation looks something like this. Cp times ln 1 plus 2 gamma, gamma plus 1, and 1 square minus 1, okay, and multiplied by 2 plus gamma minus 1 and 2 square divided by gamma plus 1 no, m1, of course, not m2, m1 square, and minus r times ln, the pressure ratio. So this is equal to 1 plus 2 gamma plus 1, and m1 square minus 1. So now we do have an expression. This is an expression for the entropy change across the shock wave, and it is a function of inlet Mach number as well. Once we know the inlet Mach number, we can, and gamma, of course, we can directly calculate the entropy change. One thing I would like to also remind from yesterday, the most important point. So just let's remember this as well. Just to remind you, what was our starting point? What was the physical, let's say, baseline or physical reference point that we started to use towards obtaining normal shockwave relations? It was the Prandtl relation. Okay, if you remember, A star does not change in an adiabatic flow, so this means that even if there's a shock wave, A star will remain constant, and A star was equal to U1 times U2. So velocities in a one-dimensional flow, the x component of velocity is U. So U1 is before the shock wave, U2 is after the shock wave, multiplication is A star, and that is basically a constant. We call this the Prandtl relation, Prandtl equation. And this actually turns out, we manipulated this a little bit to look like m1 star multiplied by m2 star is equal to 1. Okay. So, and what was m star? Let's also remember this. M star was the ratio of the local velocity to the speed of sound at star condition, at sonic condition, that is. Okay. And M1 and M1 star and M2 star are different. M1 star is not equal to M2 star because the velocities are different, but A star is constant. So therefore, in order for our conservation equations to hold across a shock wave, meaning in order for the continuity equation, the momentum equation, and the energy equation to be valid across the shock wave, this equation must be satisfied. That's the main physical driving force. Well, this was our starting point, to remind you again, and this starting point resulted in all the equations that we have been talking so far. Right now, the entropy relation, and before that, the temperature ratio, the pressure ratio relations, and the density ratio relations. They all started from here. Okay, so therefore, again, so this is very important concept, the characteristic Mach number and the associated sonic condition properties like T star and P star and rho star. This, and of course, definition of M star, very critical concept in compressible aerodynamics. Okay, now that we have S2 minus S1, the entropy change across a shock wave is written in terms as a function of M1 only. Okay, and the second law, because of the second law says this. First of all, this is an irreversible process. It is adiabatic, but it is irreversible. It's a non-isentropic process. We do know that this must be positive. So S2 minus S1 must be greater or equal to 0. If it's equal to 0, it's an isentropic process. If it's non-isentropic, it must be greater than 0. Is this really the case? So we will check that now. Is this really the case? Check that where, using what? Using the using this equation, actually. Using this equation. So in reality, it's only a function of M1, that equation. If you plug in, for example, M1 greater than 1, any number that is greater than 1 into that equation, you will see that that produces, in reality, an entropy rise, I mean, an entropy change S2 minus S1 delta S, a positive value indeed. So this is consistent with second law. We have irreversibility, second law obeyed. We have irreversibility, and if there's a supersonic inflow to the shock wave, that creates positive entropy rise. If you plug in M1 less than any number that is less than 1 into that equation gives S2 minus S1 a negative value, okay, which basically violates the second law. So normally we do not expect entropy reduction from as a result of an irreversible process. So this violates second law, which means physically that this is not possible, okay? Which means that a subsonic inflow, so M1 less than 1 is a subsonic inflow, cannot generate a shock wave. That's basically what it means. We cannot create a shock wave if upstream flow is subsonic. This is the message we got from the second condition. Another condition is that what if M1 is equal to 1? If you plug 1 into that equation actually gives 0. So S2 becomes equal to S1. So it is actually, there's no entropy change. Okay, so this condition is very special condition. Okay, generally in real life applications, when you're flying or designing vehicles that will fly supersonically or transonically, let's say, we do not M1 equal to 1 is not a design Mach number. That's how I can put it. So either we keep the design Mach number at subsonic speeds or at supersonic speeds, even if it's within the transonic regime. We don't fly exactly at Mach 1 because it creates other complexities we will see later. So basically it makes sense. I mean, what makes sense, this entropy equation is a consistent equation. It obeys our observations in nature, and also consistent with the second law as we know it. Now, going back, let me scroll up. Going back to here, our list of variables after the shock wave. Now we know this one as well. So we have an equation. So our list is pretty much complete, except for the stagnation pressure. Our list is very much complete. So now the final point, what happens to the stagnation pressure across a normal shock wave? So in order to understand that, we will do a conceptual discussion and relate it to stagnation pressure in reality. So the conceptual, let's investigate this for a second now regarding stagnation pressure. We do have a normal shock wave, okay? And we have state 1 and state 2 before and after. So let's assume that we have some kind of fluid particle at a certain entropy level S1 and moving with, let's say, Mach 1 at state 1. Let's assume that we bring this fluid element adiabatically to rest, okay? Or in fact, maybe I should directly say isentropically to rest before the shock wave. So so this is kind of a hypothetical experiment, like an imaginary experiment. So let's say I brought this particle to rest, 0 velocity. So M1 becomes 0. Let's call that state S1A, for example. Still, we haven't reached the shock wave. So If you remember from our discussion from yesterday, this does, I mean, the conditions before and after the shock wave can be investigated using isentropic relations. We have discussed this. So if I take this fluid particle and bring it to rest, basically it zero Mach number. It will be an isentropic process. So therefore, S1 and S1A will be equal to each other. So let me write that down. So fluid element, let's say, fluid element brought to rest. Rest means zero Mach number, isentropically, from state one, So it reaches state 1A, where its Mach number is actually 0, and then it is we did that isentropically, so S1 is equal to S1A. Okay. Now let's go to the downstream location of the shock wave. So let's assume again we have a similar fluid particle now moving with M2. It does have an entropy level of S2. Now we bring this one to stagnation. So in another imaginary experiment, it reaches now a state S2A, and fluid element is brought to rest. So similar text I can write here, brought to rest starting from state 2, M2 is equal to 0. So isentropically, of course. So because between 2 and 2A, there is no shock wave or anything like that. So again, it's an imaginary experiment. Isentropically, I brought it to rest. So S2 also must be equal to S2A. Okay. Now, basically what I can do is I can actually, I mean, since we already have an entropy equation, we just derived up here, up above in this page. Basically, and that gives me a relation between S2 minus S1. We already obtained it. So that will actually be equal to this S2A minus S1A, because S2 and S2 is equal to S2A, S1 is equal to S1A. So I can write this. And in fact, in terms of these temperature ratios, I can write a similar equation like ln. I mean, since I can write that, I can actually write T2A divided by T1A minus R times ln P2A and P1A. I can write these as well. Now we know one fact. These states at 1A and 2A are what we call stagnation states, because Mach numbers are 0. The fluid is not moving at that state. M1 is 0 at that state, and M2 is 0 at that state. So basically, how am I going to use this information? Basically, it means that, for example, T2A, so I see T2A in this equation, right? Temperature at state 2A, where it is actually at rest, the fluid element is at rest, it's not moving, it's the stagnation state. The static temperature, and in the entropy equation, we do use static temperatures. But since this is a stagnation state, static temperature is actually equal to the stagnation temperature at that point. So T02. Okay. And similarly, I have P2A, static pressure at 2A, but since it's the stagnation state, the fluid is not moving, it's also equal to P02. Okay. I can make similar arguments for T1A and P1A, and T1A is also a stagnation condition. So this is equal to T01, and P1A is equal to P01 because of the fact that it's a stagnation state. But okay, then what? Well, now we have an important, let's say, reality in a shock wave. Then the reality is that T02 is equal to T01. We know that. Okay, T02 equals, that does not change. That does not change. So basically, uh, so therefore, in this equation, for example, this one, this T2A is equal to T02, T1A is equal to T01, so it becomes equal to 1. So it becomes Cp times ln1. Basically, ln1 is 0, so this term actually disappears. So across the shock wave, we know that this is true. Then basically, I can write S2 minus S1, so which is equal to that, S2 minus S1. Basically, okay, let me write that down. So we will keep that also in the video here. So Cp ln T02 over T01, this term will be 0, and minus R ln P02 over P01. How did I, so how was I able to write this? Because of these arguments that we made up here. But this term is actually 0 because T02 is equal to T01. It makes it Cp times ln1, so it becomes equal to 0. So I end up with an expression that relates the entropy change, which is a function of inlet Mach number. We have just seen it in the beginning of this hour. And on the right-hand side, it should be equal to minus R times ln P02 over P01, the stagnation pressure ratio across the shock wave. This is nice because this is exactly what I was looking for. The stagnation pressure, how it changes across the shock wave. That was the last question or last parameter that I was after in order to find an equation. So therefore, I take P02 over P01 ratio to the left-hand side of the equation, P01, and then, so it becomes equal to now e to the power minus S2 minus S1 divided by the gas constant, okay? And so this equation gives us how the stagnation pressure should change across a shock wave, and it totally depends on this entropy change, which is a function of Mach number m1. So as soon as somebody gives you the flight Mach number, this can be calculated. We do know the equation for that. You plug in that numerical value here, and then you directly get and take the exponential, and you directly get the stagnation pressure ratio across the shock wave. The question is the stagnation pressure ratio now, will it be increasing or decreasing across the shock wave? Well, we do know one fact, S2 minus S1 is a positive number because for incoming supersonic streams. We just made its discussion a few minutes ago. This is a positive number, and R is a positive number. So we are talking about e to the minus a positive number, okay? So therefore, so it's basically 1 over e to the power a positive number, yeah? And the value for e is 2 point something to e. So if you take the power a positive number, so it will basically generate a number. The right-hand side will be a number that's going to be less than 1. Okay, so which means that for positive entropy generation, which is the case for a normal shock wave, P02 over P01 will be less than 1, which means there will be a drop, a reduction in stagnation pressure once the flow is passive, flow passes through, the supersonic flow passes through the shock wave. Well, is this a surprise? No, actually. We have discussed it, I don't know, maybe last week when we were discussing conceptually what happens to stagnation pressure in an adiabatic but irreversible flow. If you remember, we were discussing streamlines like that, okay? And for an adiabatic irreversible flow, since it's adiabatic stagnation temperature, I mean, regardless of the fact that whether there's a shock wave or not, irreversibility can be generated due to any reason. In this case, it's generated due to the shock wave, but it can be generated due to a variety of reasons. If it's adiabatic, first of all, T0 will not change. But if there is some irreversibility happening between 1 and 2, okay, for whatever reason, in this shock wave, or in this subject, that reason is the shock wave. The shock wave generates the irreversibility. But it could very well be, for example, it could be, and by the way, okay, it could be, let's say, some viscous effects. I don't know, a supersonic flow going over, let's say, a body, and due to viscous effects, you could having some irreversibility effects because of boundary layer and friction between the fluid and the solid and everything. So for that case where we have, for this case where we have adiabatic but irreversible flow, and irreversibility is again due to the shock wave in this case, P02 will be less than P01. We have discussed this some time ago, maybe a week or so, maybe last week we discussed this. And now, so it was not surprising when so this is not surprising when we obtain this. The stagnation pressure must get reduced, must drop across a shock wave, okay? But now we know better, we know more actually. We know how to calculate it as well. This is just concept. We know that the stagnation pressure must get reduced, but now we also know how to calculate it, and as a function of inlet Mach number, which is very nice because this is this is very consistent with all the equations that I have relating after the shockwave properties to before the shockwave properties, and all the equations are written in terms of only one parameter. If you forget about gamma, of course, only one single parameter, which is the inlet Mach number. Once you know the inlet Mach number, you can directly obtain all the flow properties the ratios at least across the shock wave. If you would like to know the exact values of parameters, like not the ratio like P02 or P01, but the actual value of P02, of course you need to know P01. So in those cases, once we know the inlet conditions to our shock wave, to the normal shock wave, we just invoke all these equations that are functions of inlet Mach number, calculate the ratios, or as I said yesterday, just go look it up from the tables that exist at the back of your book or on the internet, normal shock wave relation tables, and then given inlet conditions, you can directly calculate the conditions after the shock wave with all kind of parameters: the Mach number, density, temperature, pressure, static pressure, stagnation pressure, entropy, and of course stagnation temperature, which does not change. We have everything after the shock wave. So basically this completes that discussion, because now that we know how to calculate the entire flow field after the shock wave, after a normal shock wave, that is. And normally the free stream conditions, again, let me reiterate this from yesterday, M1, yes, must be given. M1 is your flight Mach number, and generally flight altitude is given, which gives you ambient temperature and ambient pressure, and these two will give you ambient density. So basically, these two conditions, flight Mach number and flight altitude for a high supersonic flying aircraft, for example, once these are given, you know basically all these parameters, okay? And so also from these two, you can calculate S1, and from these two, you can calculate T01. From M1 and P1, you can calculate P01. You're basically set. And then you basically implement across shockwave relations. You get all of your list of parameters after the shock. So only thing that you know is your flight Mach number, flight altitude for a supersonic flying system, whether it's a fighter aircraft or a missile or a rocket or whatever. Okay, that's good. So let me see where we are in the notes. Yeah. Now we will actually continue next week, but I will make a brief introduction in our remaining time to the new concept. Until this point, we have obtained many equations, starting with the control volume application to a normal shock wave. We obtained all these relations for a specific type of shock wave, which we call a normal shock wave, which sits 90 degrees towards your streamlines, basically. But of course, depending on the geometry that is supersonically flying through air, the shock waves that are generated are not always normal shock waves, okay? In fact, and if you remember from the videos that I showed you from last week, what we observe is more like shock waves that are not normal. I mean, in some applications, we do have normal shock waves, like whenever we have what we call a bow shock, just in front of a space vehicle that is re-entering the atmosphere. It's a blunt body. Right in front of it, we will have a bow shock wave, and most part of the bow shock wave actually acts like a normal shock wave. But for aircraft or missiles that are flying at supersonic speeds, mostly what we see just in front or actually just attached to the nose of those systems is what we call an oblique shock wave, okay? So the angle is not 90 degrees. So oblique shock wave physics is a little bit different, but or let me put it this way, it has overlapping physics with normal shock waves, which we will actually make use of the equations of normal shock waves in the calculation of oblique shock waves, but there are certain physical differences regarding oblique shock waves. And also, there is another physical concept which is completely different than, which occurs in supersonic flows, which is completely different than shock waves, so oblique or normal. Those are called expansion waves, okay? So now we will start, I will make a brief conceptual discussion today in our remaining time, but we will actually start talking about them next week, continue next week. So we will now expand our discussion to oblique shock waves and what we call expansion waves. Okay, see, none of these physics exists in subsonic flows. Normal shock waves, oblique shock waves, expansion waves, none of it exists. So it's that's why compressible flow physics is, you know, a separate topic we need to spend quite a bit of time on. The flow physics is, and let's say flow physics is very much different, but so we need to make use of, let's say, proper set of equations. Our main conservation equations are the same, whether it's subsonic or supersonic, but some specialized care need to be taken. So the simplest case which we can use to explain An oblique shock wave is when we consider a supersonic flow over a wedge. So let's say a wedge is like this triangular object, okay, sitting somewhere in the supersonic stream. So this could be the nose of your missile or the nose of your fighter aircraft, whatever. So we have a free stream Mach number greater than 1. So this wedge is subjected to a supersonic stream coming towards it. And let's say this is the center line of the wedge. Okay. So we have, again, if flight Mach number and altitude are given, we can calculate our list of variables again before at the upstream of this wedge. Now, what happens is this wedge, this solid geometry, is not a blunt geometry, meaning that it does have a certain angle from the center line, theta. So that theta is not 90 degrees. If it's 90 degrees, we call it basically or 45 degrees by this definition. So 2 theta is 90 degrees. If it's 90 degrees, we call it a blunt surface. But this is not. This has a very sharp nose and a very finite amount of theta that is less than 90 degrees. When a supersonic flow meets this kind of geometry, or I can explain it the other way around, when an aircraft that has a certain shape like this is flying at supersonic speeds in air, what happens is and if you again remember the video that we have seen last week, I think it was on Thursday, and actually we will discuss the physics about it next week as well. The fluid particles sitting here, they do not know some object is coming towards them, because the information or the disturbance created in the fluid medium is propagated by the speed of sound, but this vehicle is flying faster than the speed of sound. So before the particle knows that there is a vehicle, it's not aware that somebody is coming very fast towards it. So, but as soon as and this is moving in let's say in a streamline. But as soon as there's a wedge, for example, with the theta angle is there moving, or as soon as the particle senses this, it needs to adjust its direction almost instantaneously, because at least it must be flying parallel to the wedge, because that's the solid body is imposing that. Now, this condition can only happen through a shock wave which is sitting at an angle and attached to the nose of this wedge. And if it's symmetrical, if it's coming in at 0, let's say, angle of attack, it's symmetrically, we have also a symmetrical shock wave at the bottom here. Okay. Now, this shock wave with respect to the incoming streamline is not at 90 degrees. So this angle is not 90 degrees anymore. So this is not what we have learned so far. This is not a normal shock wave. And we actually use the Greek letter beta to define the shock wave angle with respect to this center line of the wedge. So theta is what we call the wedge angle. That's actually, it's the angle of the geometry itself, and beta is the angle of the shock wave, oblique shock wave itself, and that is not 90 degrees. So these kinds of shock waves are known as oblique shock waves. Okay, this is an example of an oblique shock wave. And we in this kind of flow situation, we also would like to know if I know the flow state or the gas state at 1, what happens to the gas state at 2? and knowing the fact that this is not a normal shock wave, the angle is different, okay? And in this case, so this could happen. So what happens to this, we will see. But this kind of oblique shock waves also happen. So the example here was a wedge, kind of representing, it could be representing the nose of an aircraft or whatever. But also it happens in situations like this. For example, let's say this is a wall. So we have a wall here. Over the wall, we have a supersonic stream, M1 greater than 1. And suddenly, somewhere here at the wall, we have what we call a ramp. So like something like that. Okay, sudden angle change in the geometry. This kind of geometry, sudden geometry change also creates an oblique shock wave right here, okay, at the corner. Now, and again, we would like to know the conditions before and after, and the ramp angle. This is also defined as theta, and this angle is also defined as beta. And so this is not a wedge now, this is basically a ramp.